changes so that these bottlenecks do not appear. But it's very difficult to keep updated because these companies do not reveal the architecture of GPU. So that's why I'm discussing this point. Because many of the papers you will read, they would have mentioned this issue. So first is control flow divergence. So if you remember, in approximate computing, we discussed this idea how we can use branch herding to avoid different threads going on different if and else path. For global memory, we can do memory access coalescing. That means we have to do memory access coalescing. And for shared memory, we should avoid bank conflicts. So here is an idea. So what is control flow divergence? Suppose sometime whenever we have any if switch condition, if or switch conditions and so on, for sometimes either one condition will be true and another time another condition will be true. So now when you have a var, so what is a var? So var means many threads will do lockstep execution. Okay, lockstep execution means they will work together. That means if so we talked about the barrier synchronization idea. So that means they will, if here that means we have implicit barrier synchronization. Right, we have this implicit barrier synchronization. So after this point, only when all the threads have reached this point, only then you can make further progress. So if some threads are going on the if part and some threads are going in the else part, then when some threads are going on the if part, other threads will remain idle. They cannot at the same time execute out the else part. Okay, because all the threads will do the same thing. That's the idea of lockstep execution. All the threads will do the same thing. If some of the threads cannot do, if some of the threads don't have to do the same thing, they will have to remain idle. They can't do anything else. They will have to remain idle. Okay, so that's the idea. So we want to avoid this. That means we want to have as minimum as possible this kind of scenario. And that's why GPU is not good whenever you have a lot of control flow dominant code. That means if you have simple code where all the threads have to do just simple thing. So for that, GPU is highly optimized. But for this kind of scenario, GPU is not good. You have to use CPU. Okay, you have to use CPU. So that's all on branch divergence or control flow divergence. We should avoid control flow divergence as much as possible on GPU, because then parallel computing does not give you much advantage. Now, on global memory, we have to do memory access coalescing. What does it mean? It refers to combining multiple memory accesses into a single transaction. So here, every successive 128 bytes. So we have, for example, a VARP has 32 threads. In some examples, I will take just example as a VARP has only 16 threads, but in general, VARP has 32 threads. So each thread accesses one word. One word is 4 bytes. So total, a VARP is accessing 128 bytes. Okay, so VARP has 32 consecutive threads. Each thread accesses one word. One word is 4 bytes. So one VARP is accessing 128 bytes in a single transaction. So, but if you have following conditions, it will result in uncoalesced load. That means memory access, they become serialized. Okay, so one is memory access is not sequential, memory access is sparse or misaligned memory access. So here is an example of all this. So first of all, we have 32 consecutive threads, they access 32 consecutive words. Here memory access is sequential and aligned. Therefore, it is coalesced. That means a single instead of sending all these requests, we'll send a single transaction, and that will bring all the data. It is just like, there are some small merchants and there are large merchants. Large merchants will always take large orders. They will not take small orders. So similarly, global memory, it always take large orders. It will not take. I mean, if you send it individual request, it will not be efficient. So here, memory access is sequential and aligned. Now, here is an example. Memory access is not sequential, right? Here, you're not accessing it sequentially, but at least it is aligned. Aligned means whether it is fitting in the boundary. Aligned means it has to fit within the boundary of 0 to 127, 128 to 255, 256 to the next, and so on. So in recent GPUs, of course, this is not a problem, as I already said. But so forget recent CPUs. So this point you can ignore. We just have to worry about the GPUs on which we are focusing. So here, these accesses are aligned, but they are not sequential. Here, they are in between. They are not sequential. See, if one of these accesses were to go outside, then you can say it is not aligned, right? But as long as you're staying within the boundary of 0 to 127, 128 to 255, it is still aligned. Now, here is an example of this access is sequential because every thread is accessing one after another, one after another, but it is not aligned. So it requires one transaction to load first 31 words, green words, and another transaction to load the last word. So for now you need two transactions, which is why it is not efficient. Okay, so is it clear for everyone? And any questions here? Fine. You understood what is the difference between sequential and aligned. An access could be sequential plus aligned. An access could be sequential but not aligned. An access could be not sequential but aligned. And an access could be neither sequential nor aligned. All those four possible combinations are possible. So here I will take example as if a bar has only 16 threads. Okay. The idea is same. It is just we are reducing the number of threads in a bar. So here coalesced reads. So here float means we are accessing a 4 byte. Every word is 4 bytes. So here all the accesses that we are accessing, all the addresses that we are accessing, they should be in a region of 64 bytes. So here starting with 128, it is all finishing at 191. So that is sequential plus aligned. Here, some threads are not participating, but that's not a problem. It is still aligned. It is still aligned access. Okay, we'll get some extra data. That means we will send a single transaction, which will get extra data, and some of the data which comes, we will ignore it. That means the data which is coming from here and here, we will ignore that data, but that's fine. Now here it is overlapping accesses, which is again no problem. Because we are not fetching extra data, we are still making single transaction. Some of the data which will come, we will ignore it, but that's not a problem. Now, here it is misalignment, right? Here we need to make more than one transaction. We are crossing the boundary, right? We are crossing the boundary of that 64 byte chunk here. So, anyone has any questions? So, if you have this kind of access to global memory, it will not be efficient access. Here is an example of the code. So, a coalesced memory access instruction looks like this. For example, we are reading from global memory, okay, to shared memory. So, here, I have not taught what is this, so you can ignore it, but at least you can know about thread index. This part you can ignore. What is blocked? It doesn't matter. You can ignore it. So thread ID. Every thread is accessing one memory address. Okay. But if you have a stride of 4, okay. So again, you can ignore this part. I will not include it in the homework or exam. If you ignore this part of the code, so here first thread is accessing 0, right? Next address, next thread is accessing 16, because if you know pointer, how does pointer computations work? If you don't know C++, I think you will not know. Suman, please mute yourself. So in C or C++, how does pointer computations work? So for example, if you have a suppose int pointer a, suppose you have int pointer a, right? Suppose int a is equal to some address 1000. Now if you do a plus plus, what is the value of a now? Tell me. Anybody who knows C or C++ can tell me.
1001.
Priyansh, no, it will not be 1001. Otherwise, it will be very trivial answer. You are moving on the next integer now.
Okay. 1004.
Yes, 1004. Because integer is 4 byte. Right? Integer is 4 byte. So when you do a plus plus, it moves to the next pointer location, which is 1004. Yeah, 1004. Okay. So similarly here, when it is correct, but thread number 0 will access 1000, thread number 1 will access 1004, thread number 2 will access 1008, right? So they will access at a difference of 4 byte. So that was the case here. That was the case here, the first case. The thread 0 is accessing 128, thread 1 is accessing 132, thread 2 is accessing 136, thread 3 is accessing 140, and so on. Whereas here, now you tell me what will happen. Instead of 1000, what will it change to? What will thread 0 access? What will thread 0 access here? It will still access 1000, that's fine. Okay. Now, what is the next? What is this next one? It will be now 1, a value of 1, which will get multiplied with stride. So that will become 4. So whatever was thread 4 accessing now, that will be accessed by a thread value of 4 that was accessed. So now it will be, this was 0, 1, 2, 3, 4. So that will be 1016. Okay, so it will no longer be sequential or aligned. It will cross the boundary. Right?
Sir,
because, yeah, just 1 minute. So here we multiplied the thread value by the stride. So now our this value will become 0, 4, 0, 4, then 8, 12, 16, 20, and so on. And corresponding to that, if you find out the addresses, so for 0 it will be 1000, for 4 it will be 1016, right? For 8 it will be 1032. Okay. For 12 it will be 1048, and so on. So it will cross the boundary. Yes.
Sir, so we are using stride as a multiplication factor to access different, like, to point at different locations.
Yes. That is the meaning of stride. Stride shows how much you are jumping.
Sir, but here we are by ourselves misaligning the
memory. So, yes, it's not that there is some evil person coming in the night and changing your code. We have some programming feature which is not efficient for the hardware.
Sir, what are we meaning by this word coalesce?
Coalesced, I explained, right? Oh, this memory access coalescing. That's what I'm discussing. Coalescing. Here, what is the coalescing? Coalescing means can you issue all this in a single transaction? It is coalesced. This access is coalesced means merged or amalgamated. That is the meaning of coalescing. Coalescing means can you combine them into a one. For example, like if you see, like many people from Roorkee, they will be giving their orders on e-commerce website. So there will be some local. They will have some local, processing or local go down. So that means all the orders coming to Roorkee must be going through that Luxor. Luxor is a very close city, or Haridwar. Let us talk Haridwar. So suppose Haridwar is the nodal point. All the orders which are coming to Roorkee must go by the Haridwar. So it's not that Haridwar center is issuing one order by one order, one from me, one from you. No, all the orders they get, they must be combining it. And once it comes to Haridwar, it will spread to all the locations in Roorkee individually. So Haridwar is making one single order to the e-commerce, central go down. And after it comes to Haridwar, you're sending one by one. So Haridwar is coalescing all the orders.
Okay, sir.
Fine. Is it fine?
Yes, sir.
Any other question?
Yes, sir. In unaligned axis, sir. Next slide, sir.
Yes. So this is aligned. This is not aligned. Yeah.
Yes. So thread 1, so thread 0 has to be. How we decide to 128 is the alignment. It should be multiple of 2 or 4. This power.
Yeah, that's a good. No. See here when you have 32 threads, it should be aligned. So 32 into 4 is 128, right? So then the alignment boundaries are 128. That means 0 to 127, then 128 to next 255, then 256 to 256 plus 128. And in this example, where we took that one warp is only 16, here it should be the boundary of 64.
So if we take from 1 to 129, that's unaligned.
Yeah, exactly. 1 to 120, that is unaligned.
Okay, sir.
And any other question? Okay, let's go forward. Now coming finally to shared memory. So shared memory, many threads will access the shared memory. As you know, shared memory is shared between which threads? Anybody remembers? Shared memory is shared between which of the threads? Threads of one dash dash dash.
So between the blocks.
No, threads of a single block, not blocks, not plural
yes.
block, but threads of a same block, they share the shared memory. Yes. So memory is divided into banks. Okay, it is just like that. Like suppose my room currently has only one door. Okay, so one door means only one person can enter at a time. If multiple people want to enter, they have to serialize. That means one person will enter, then next, then next. Parallelly, they cannot enter. Okay, so here memory. So now, if you want to allow parallel access, then what they do, for example, especially some of the centralized offices where there are a lot of people coming in, coming out, they divide into multiple rooms, right? One room for one room for undergraduate related services, one room for postgraduate related services, one room for alumni relations, right? So that's a rough idea. So similarly here, we don't keep a single monolithic memory. We keep our shared memory divided into multiple banks. Each bank can allow one access. So if there are 16 banks, we can simultaneously issue 16 requests, which allows us to have high bandwidth. Okay, memory is divided into banks. Each bank can independently serve one request in a single cycle. So, here it is. Each bank can service one address per cycle. So a memory can service as many simultaneous accesses as it has number of banks. Okay, so this bank idea is used to increase the bandwidth. But if there are multiple simultaneous access to a single bank, they result in a bank conflict. Okay, so conflicting accesses are serialized. That means if more than one person tries to access one room, or here in this example, more than one request is made to a single bank, that will be serialized. That means if you have 16 banks, how many maximum requests can we serve in a single cycle? Shivanshu? If we have 16 banks, how many maximum requests can we serve in a single cycle?
4 into 16, sir?
4 into 16. Anyone else? How many?
Sir, 16 only, sir?
Yeah, exactly. 16 only, right? Every bank, see, it's written on the slide. Every bank can service one address per cycle. That means one request. Now, each of that request can be, a 4 byte. So please remember, one bank means one request per cycle. Okay. So here in shared memory, our optimization is that we should not send multiple accesses to a single bank. Okay. Conflicting access will be serialized. So here now no bank conflicts. All threads are accessing separate banks. Then it is no problem. Here also no conflict. Random permutation. Different threads are accessing different banks. Which is not in any order, but at least it is still two different banks. Here it is a two-way bank conflict. So thread 0 and thread 8, they are accessing single bank. Thread 1 and thread 9, they are accessing a single bank. So half of the banks are getting 2 accesses each, and half of the banks are not getting any access. And this is the 8-way bank conflict. Here, 8 threads are accessing one bank, another 8 threads are accessing another one bank. So here, compared to normal case, which was this, in this case, latency will increase by 2x. And here, latency will increase by 8x. Worst case latency, right? Because some of the banks are not getting any access, so they will take 0 cycle. But bank 0, that will take 8 cycles. Here, this bank will take 2 cycles. Okay. So you will have to write your code accordingly so that these conflicts are reduced. Is it fine? Any questions?